notion of like entity, putting this notion in the model is very useful for this kind of discrete behavior of language that we need. These kind of models, therefore, offer this attractive property, but then, on the other hand, they have no clue about what it is to mess up or what it is to be a brother. Like, they really, these kind of nuances, which for people in computer vision, it may remind you of like defining what a cat is in terms of, necessary and sufficient conditions. You cannot do that, right? It's really something where you need a highly dimensional and graded notion to be able to account for this kind of also very fundamental part of language. And this is where continuous models come in handy. So we can get lots of data, crunch it, turn it into some high dimensional representation, and get something that really approximates in really useful ways the meaning of the word brother or even mess up, and also cat. There always has to be either a cat or a dog in talks by people working in NLP with this kind of representation. So that's my cat. There won't be any other. Okay, so as you can see, standard models in natural language processing, they have word representations. They have something to process sentences. Nowadays, with recurrent models, we can process sentences and longer discourses, but we don't have a notion of entity in the model. This notion of like the real thing in the world that we are talking about. And so our proposal is to do precisely that. So we're going to add a module to represent entities. And the idea or hypothesis is that jointly learning to represent language and the entities that it talks about will improve computational models of both. This is the hypothesis. We just completed the initial phase of the project. And one of the things we've done is to participate in this international competition, Semeval 2018 Task 4, which is about character identification, which is this referential task in which we get dialogues from the TV series Friends, and we can get something like this: Joey saying, "See Ross, because I think you love this woman." And in this data, each mention of a character, like Ross, I, you, or woman, is tagged with the ID of the character it belongs to. Like Ross, for instance, is character number 335, and both Ross and you have the same ID. Unfortunately, this is all the this is all the information we have about the characters, just an ID. So everything we learn about them has to be learned from the dialogue data. And in the future, we may be able to work with video. I hope that in some future edition, I can tell you something about this. But for the moment, that's all we will be working with. Language, and then some ID, and then we have to infer something. However, if you want images, like grounding language in images, I advise you to go to the poster session tomorrow at 1 p.m. at UPC, if you can make it there. I hope many of us can make it. And talk to the PhD student of the project, Yunus Shoradok, who will be presenting some cool work that he's been doing with colleagues at the University of Trento. All right, so back to the task I was talking about. This is the task, and there's about 400 characters, and we also get this typical distribution of a lot of human behavior that Jordi Pons was talking about this morning. Also, no, Jordi Pons, was it? Uriol Nieto, I think. Well, this thing about the long tail, where we have 6 main characters that are mentioned a lot, and then we have a long tail of like infrequent characters that we don't have a lot of data for. And as we all know, deep learning methods are super data hungry, and current methods can do very well on really frequent things and really very badly at infrequent things, which in terms of types are the most frequent. We have the usual paradox, at least in language, that we have this Zipfian distribution, and in a lot of other human behavior. The evaluation measure that the organizers put, I think, is a very reasonable one, in which you get a macro average F-score, in which all entities have the same weight. That means that you cannot cheat. You cannot just do well by doing well on the main characters. You really have to account for also for infrequent characters. All right, in terms of model, we start with the workhorse until now, until the transformers. This has been the workhorse of natural language processing, an LSTM. In this case, it's a bi-LSTM, bidirectional LSTM. It's just a recurrent neural network in which we get some input. In our case, we have the speaker as input, and then each token in the given utterance. And this is processed word by word. And this is turned into some kind of, do I have a pointer? Yes, I do. This is turned into some kind of abstract representation. The whole thing is modeled here in the hidden layer. And from this abstract representation of the whole utterance, we go to a probability distribution over the classes here. So we treat this as a classification task where we have 401 classes. And you can train it normally via backpropagation because you have the ground truth with one-hot vectors. Okay? So this is the basic model that we will be starting from, and then to that model we will be adding a memory. Very primitive sort of memory. It's just a static memory, just a set of weights that you also train by backpropagation. And here what you do is we have a further mapping from this general representation of the context. We have a further mapping, and this, for instance, when we process U here, we get this representation of the whole utterance, and then we extract a representation of what we hope will be like this mention. And this gets compared to each of the entities in this static memory. How do we encourage the model to actually store entity representations here? By tying these weights to the output classes, all right? Because, for instance, this vector, will be, the mapping will transform it into this, there's representation here, then this one here will be Ross, which you may remember, 335 is Ross, okay? So the idea here is just a simple attention, for those who are familiar with that, it's just a simple attention over the static memory, and then you get these scores that tell you, which one is the most probable character in this context, all right? We also test, one very neat thing of having this type of architecture is that we can have sharing, like basically here, for instance, so we have entities in two places in the input. We have entities in the way people talk about things when you say I or you or woman, these are entity mentions. But we also have entities in the input, right, in the speaker. Like Joey is an entity whether he speaks or is being talked about. And so what a very neat thing that we can do here is to tie the representation of the speaker with also this entity module, where we are having a single representation for entities, both on the role of speakers and on the role of, somebody talking about them. And we will see that this is crucial for performance. All right. We also tested a model that was proposed 2 years ago, that's prehistory, that adds a dynamic aspect to the memory, which is these values. So this is really a static memory, that only gets trained via backpropagations. That means that, for instance, at test time, the properties that are encoded here do not change. Whereas here, it has a dynamic component that can vary during the utterance. However, this component this component here turned out not to be used in our experiments, so everything I'm going to say is common to the two types of memory that we have tested so far. All right, so here are the results. So we won the competition. Only 4 teams participated, but it's always neat to win. As you can see, the F-score is still low. It's a challenging task, and it's also a very, very strict evaluation measure. So accuracies are about 70-something%, but this F-score measure is 40, ours was 31. And this was the model with the static memory. And in work in progress, we are pushing the numbers up. And we still, crucially, so this is our best model, the model that we sent to the semi-level competition, 41. This was the second best model that used a completely different architecture, much more complex, actually. And this is the BiLSTM without a memory. So the gap between having or not having a memory is pretty large. And in current work, we are pushing the numbers up, as I was saying, and still the same difference between having or not having this module is there, okay? And note that this does not, this gain does not come at the expense of model complexity, because, you can always add more parameters, more complexity, and then maybe things will improve. But here we have essentially the same size for all 3 models and still a large gap in performance. As you can see, the 2 types of memory perform essentially the same. moreover, what's very nice is that we are doing better. Actually, the three models do the same on frequent entities. In fact, the dumb model has a bit the edge. But then the BiLSTM really, the performance drops really dramatically for medium and low frequency entities, whereas ours really still degrade much more gracefully. So we were happy. We thought that we had gotten some support for our hypothesis, but it turns out that we do not, at least for the moment. So we cannot say hooray, because this memory that we like to look at as an entity library, as a storage of information about entities that we learn directly from data and this and that, is not doing what it's supposed to do. How do we know? Well, what we did, so we wanted to test whether these learned, we thought, entity representations, whether they were storing real information about these entities. And what we did is to go to a wiki page, semi-structured data, and we extracted attributes of entities from this wiki by parsing it. So we could extract information such as the fact that Ross's gender is male, he is a paleontologist, the brother of Monica Geller. So basically data about gender, occupation, relationships, and relatives. And then using a very simple pattern grammar, we converted these attributes that we extracted from here into sentences, like this person is the brother of Monica Geller. And these are descriptions that uniquely identify a character based on his or her properties extracted from the wikia. And we can use the models as is, because in the end you can treat this as a character identification example. So we don't have to do anything special. And here are the disastrous results. We are basically at random, almost zero accuracy, all models alike. And that means that we are not encoding even like such basic information as gender is just not there, which is important, for instance, to resolve he or she. Okay? And we replicated this result with another setup in which we were testing the attributes, not descriptions, but really the attributes. So this is really a robust result. It's not a specific quirk of always using this person or something like that. All right, so we still hold by our hypothesis. We still think it makes sense, but it's still to be determined. So we do not have at present evidence that jointly learning to represent language and the entities it talks about will improve computational models of both, as we would like to have. Still, where does this large gap in performance come from? We are doing something right? Well, there's two aspects that make it do something right. The first one is this thing that I was saying. Because we are sharing the speaker and mention representations, we are able to emulate rule-like behavior, like I refers to the speaker. And note that here, the basic model without this module needs to independently learn the relationship between each speaker and each output class. And therefore, it can only solve I for entities that it has enough data for, right? Because it has to learn the mapping between the speaker and the class in the first place. Whereas by sharing this representation, the only thing that is needed is that the entity vectors are distinct enough, okay? And these analogies are always super dangerous, but it's not that different from, I hear somebody in the street who is totally unknown to me say, I went to the shop, and I infer, the person who is speaking went to the shop, even if I don't know anything about them, all right? So that's good. And the other nice thing is this separation, because we have this part here that extracts the meaning representation, the kind of mention representation from the generic representation of the context. And this is useful. We see it a bit as a division of labor. This one can represent the whole context with other things, like, for instance, speaker information, things like that. And this one can specialize really in the prediction task. So we are separating the representation of the context from the information that is really crucial to solving the prediction task. And as you can see here, this is a 2D representation where the colors are characters. For instance, the brown here, the brown dots are Ross, and these are all dimensions where they can be, you or Ross or Guy. They're all these little dots here. And in the hidden layer of the LSTM, the one that represents the whole utterance, there is already some structure, but it's much clearer in this layer here. And this separation of division of labor is beneficial. We get a better use of context, but that doesn't mean that it's a good use of context. It's still really bad, all right? Basically, the only thing that is encoding very well in terms of context is really the speaker. And that's why we are really bad, for instance, he and she. Now, we know that LSTMs in principle can represent context. We know that from other tasks in NLP, like machine translation or language modeling. So here, one of the issues that we have clearly is data. So there's very little data. And they're doing some kind of transfer learning pre-training, like we've seen in other sessions. That would be the way to go. The other possibility is that the signal, the prediction signal, is a bit too poor. Like more than half of the data points are things that only require speaker information, like I, my, mine, and also proper names like Ross, where it doesn't really depend on context. They're what's called rigid designators. That means there's a one-to-one correspondence between characters and names. And so the training data could be too poor, and they're adding another objective, and also combining it with transfer learning clearly is the way to go. Interim conclusion, these kind of entity-centric models, with the same size, we get better results. They are theoretically motivated, and I think that even if we don't get entity representations, they still naturally enable putting good inductive biases in the network. That means, like this thing of, for instance, sharing the representations between parts of the input and output is a principled sharing. It's not like we add one more layer and see if it works. It's really like, they're both entities, so let's share the representation. That's a principled way of going about things. So that's good. I think that these two things are good. The bad thing is that they're not supposed to they're not doing what we thought they would do. And also this thing that they're largely context sensitive, of course. And another take-home message, I think, from this piece of work is that analysis is crucial. It's not enough to have a motivation. It's not enough to implement it and to see better results. We really have to see specifically the behavior of the model and see, what each module is doing. All right, so I said that, well, we have very little data. That's not ideal in deep learning. So we applied the same idea to a very different task, language modeling, where there is lots and lots and lots of training data. You get training data for free nowadays that we have, internet and things like that. So this task is the task of word prediction. If I tell you I went to the pub and asked for, you will probably think beer or whiskey or something like that, not democracy, right? Nobody thought of democracy. And here the idea is very similar. So basically, the task of the model is clear, right? You have to predict what word will come next, given a context. And again, note that here the input are words. I went to the pub, and the output are also words. It's like beer, so it's the same thing that we have in the input and the output. And so in previous work, people showed that sharing the representations for input and output words really improved results. And it's the same idea, sharing the representation between speakers and reference in our case. And what we do is very simple. We add a linear transformation between the hidden layer and the output layer. And with a similar motivation that we had for the mechanism to query the entity library. So there are some subtle differences in the architectures, but the idea is the same. We add this further transformation, and then this, and then we tie this to the input, and we tie this module to the output classes. And this way, we can use what we learn when processing pub at input to predict whenever it comes out in the output, for instance. Okay, so it's a very similar architecture. However, in this case, the effect of this tying is much more dramatic than in the previous case, because in the end, we only had 400 speakers, whereas the vocabulary is like thousands of words. We have 50,000 words, I think, in our experiments. And so, of course, having one or two of those makes a huge difference. And in this work, it's not like, oops, sorry, oops. In this work, I am getting very messed up with the pointer. Now I got it. Okay, so here we are reducing the model size to almost half, so like 55% of the parameters. And we are getting essentially the same performance. This is language modeling, it's perplexity, so lower is better. So we see it's almost the same, but it's even a bit better performance in the task. And also, the word representations that we get are actually better. This is cosine, so higher is better. And we get 61 with respect to the previous model. And these are higher quality word embeddings, not measured on the task that it was trained for, but in a different task, in word similarity. And it extends, this extends to another task yet, but that I'm not going to go into. But if you want to hear more details about this work, again, I encourage you to go to the poster session tomorrow at UPC at 1 p.m., where Laura Aina will be presenting this work that they also presented at the MLP not so long ago. All right, so now coming to the real conclusion. As I was saying, I think that by having modules that are motivated, we can have, like, naturally put the right inductive bias for neural networks to learn. And then, as a consequence, we obtain models that can do more with less. And what do I mean by that? Well, less data. They need less data, and that's shown by the fact that we improve results on lower frequency entities in the first task, in character identification, and or with fewer parameters. And that's shown in the language modeling results that I was talking about, where we have better results with less model complexity. And this means that we are having a better use of the learning capacity of neural networks by having these, principled architectures. And going back to language, as I was arguing in the beginning, referencing language has really continuous aspects. You have to understand what mess up is, and for that you need, something that is clearly not discrete because it's a fuzzy category. And also very discrete mechanisms like pronouns, that are really very much like discrete pointers and require things like identity, which are notoriously difficult for deep learning models. And so our work goes towards modeling discrete behavior with continuous means. And that's also something common with needs in other areas of AI. If you want more, I take the chance, I hope the organizers don't mind, to invite you all to the Cold Kickoff workshop, which will take place on February the 8th in the morning in this auditorium. If you want to know more about what our research group is working on and chat about possible collaborations. Thank you.